So this is a silicon chip. It has a width of 4 millimeters on a side. And to enhance the heat transfer, we have a copper pin fin that's brazed to the surface. So the pin length and diameter, so the length is 12 millimeters and the diameter is 2 millimeters. We have atmospheric air. The velocity is 10 meters per second. T infinity is 300 K, and it is in cross flow over the pin. The surface of the chip and therefore the base of the pin are maintained, so T sub B equals 350 K. And so what we're going to want to do is, if you notice, we are missing the H. So the first thing we want to do is find the average convection coefficient, then determine the pin heat transfer rate, and finally the total rate of heat transfer from the chip. So the first thing that we're going to have to do is find our H. And it's an average one. And in order to do that, we're going to have to use a Nusselt number correlation. So, as you know, all the Nusselt number correlations are a function of the Reynolds number as well as the Prandtl number. So let's calculate this Reynolds number, V, that's the velocity. So this is 10 meters per second times 0.002 meters. And when we look up the viscosity for air at this temperature, or at an average of 325 K, we come out with 18.41 times 10 to the minus 6 meters squared per second. So our Reynolds number is going to be 1087. Now there are a number of different correlations that you can use. Again, this is a cylinder and cross flow, but the best one to use is the Churchill-Bernstein correlation. So that's 0.3 plus 0.62 Reynolds to the 1/2, Prandtl to the 1/3, there's that Prandtl number in there, divided by 1 plus 0.4 divided by the Prandtl number to the 2/3. All of this is to the 1/4. And if that weren't enough, this is all multiplied by 1 plus the Reynolds number divided by 282,000. This term is raised to the 5/8, and this entire term is raised to the 4/5. So the Prandtl number for this, for air at this temperature, is 0.704, and while we're at it, let's have the K because we're going to need it, 0.0282 watts per meter K. So when we put in our Reynolds number, when we put in our Prandtl number and solve, what we end up with is an average Nusselt sub D equaling 16.7. So our H bar equals Nusselt sub D K, as I said we're going to need that, divided by D, which equals 235 watts per meter squared K. So now that we've found our H bar, the next thing that we're asked to do is to determine the pin heat transfer rate. So the fact that we have solved for this H makes you think that this is a fin with tip convection. So the Q of the fin equals big M, the cinch of little m times L, plus H over MK, cosh of ML, divided by the cosh of ML plus H bar MK times the cinch of ML. So the first thing that we're going to do is calculate that big M. So M equals H bar pi d k. So this pi d is the perimeter, and then we have to multiply it by the cross-sectional area, d squared over 4, pi d squared over 4. And this is all to the 1/2. We multiply this by theta sub b. So this equals pi over 2, because we can pull that pi squared over 4 out of the square root, 235 watts per meter squared K times 0.002 meters, and we have it d squared and d, so that's cubed. And let's continue this on the next line, times 399 watts per meter K, and that's this K over here, which is the K of the copper, times 50K. And this part is raised to the 1/2. So what is that 50K? That's theta sub b, which is TB minus T infinity. And when we calculate this, it ends up being 2.15 watts. The next thing we have to do is calculate little m, so that's H P over K A sub C to the 1/2. And we do it exactly the way that we calculated our big M, using the perimeter and using the cross-sectional area. And actually here we can cross out some things from P over A sub C. So we're left with 4 times 235 watts per meter squared K, divided by 399 watts per meter K times 0.002 meters, and this is to the 1/2. So our little m is 34.3 inverse meters. So our ML is 34.3 inverse meters times our length, which is 0.012 meters. Actually, what we should do is make that a corrected length and add to it d over 4, but with significant figures, it's not going to change anything. And so our m sub L is 0.412. So H divided by M times K is our 235 watts per meter squared K, divided now by that 34.3 inverse meters times 399 watts per meter K. And that equals 0.0172. So why do we need all this? Well, let's go back here to our original Q sub F, which is what we're looking for. We have our big M, we have our little m times L, we now have our H bar over M times K. Now we can put it in the equation and find out exactly what our Q sub F is. So our Q sub F, and when we put in the numbers, we find that it's 0.868 watts. So that's the Q just of the fin. If we want to find the total rate, that's from the base as well as the fin. So our Q total is Q of the base plus Q of the fin, which equals H bar times W squared minus pi D squared over 4. So what's that? That's where we had to take the width and subtract from it that cross-sectional area of the fin where it is attached to the base. If we had more than one fin, we would have to multiply that by the number of fins. That's times theta b, which is just t to the base minus t infinity, and we add to that our 0.868, and so that equals 0.151 plus 0.868, which is 1.019 watts. And notice how much of that heat rate comes from the fins rather than from the base.